let's recap the method of maximum likelihood. Whenever we do this, we first want to assume a probability distribution. And then we want to maximize the likelihood that our sample data came from that distribution. So we want to find the maximum likelihood estimate parameter that would best fit the data following that distribution. Okay, so first what we need is a likelihood function. Okay, so our likelihood function for several observations, we'll call them y. Okay, y sub I. So y sub 1 through y sub n. We collect a sample of size n. Okay, and we have some parameter theta. Okay, and this likelihood function is defined as the PDF of that particular distribution that we're wanting to fit, evaluated at y1, okay, given some parameter lambda, multiplied by the PDF evaluated at y2, given that parameter theta, all the way through to y sub n, given theta. Okay? So this is defined, just the way that we're defining it, the likelihood function is the PDF evaluated for each one of those samples that we collect, or each one of those observations on our sample of size n. Okay? And so what we want to do is maximize this function with respect to theta. Okay? Theta is that general parameter from this probability distribution. For example, if we've got an exponential distribution, this theta parameter would be lambda. If we had a normal distribution that we were wanting to fit, this theta, this general theta notation would be mu and sigma. Okay? So what we want to do here is find the value of theta that maximizes the likelihood function. So what do? We use calculus. Okay? We want to find the derivative, partial derivative, with respect to theta of the likelihood function. Okay? But this can be kind of difficult to do because we have to use the multiplication rule multiple times over. Okay? Whenever we're doing whenever we're taking the derivative. Okay? That can become very difficult. It might involve the chain rule. It could be difficult to do. Okay? So what we need to do here is, or what we can do, is take the derivative, we can take the natural log of the likelihood function. Okay? If we take the natural log of the likelihood function, that means that we can sum the natural log of each one of those elements. Okay? So the natural log of the likelihood function is equal to the natural log of f evaluated at f1 plus the natural log of f evaluated at y2 plus the natural log of f evaluated at yn. Okay? So this makes the taking the derivative much simpler. Okay? Because we can take the derivative of each one of these separately and then add them up. This could be difficult, especially doing it by hand. If we had computer software, it's really simple. But if we're doing this by hand, which obviously we want to do because we're taking a class, we need to take the natural log first. Okay? And then we can take the derivative of this. Okay? The derivative of this with respect to theta, setting it equal to 0, solving for theta, here is the same. We would get the same answer as here. Okay? Whatever theta maximizes the likelihood function is the same theta that's going to maximize the natural log of the likelihood function. So we're going to take the derivative, partial derivative with respect to theta of the natural log of L. Okay? Set it equal to 0 and solve for theta. Okay? So essentially what we want to do is maximize this with respect to theta. We want to find the argument theta that maximizes the likelihood function.